Okay, so atmospheric pressure is what I want us to discuss this particular time. And we have done pressure in solids, in liquids, and now we are dealing with atmospheric pressure. First of all, I want us to, define atmospheric pressure. Then we actually look for or discuss an experiment that shows the existence of an atmospheric pressure. If you're outside there or where you are right now, atmospheric pressure is there, but you cannot feel it from your body or with your body that now I'm feeling the pressure because of the atmospheric pressure. No. But its effects can be highly felt by other demonstrations. For example, now, let's define it, then we see that type of experiment. Atmospheric pressure, as I've given you over there, is the pressure exerted on the Earth's surface by the column of air around it. The Earth's surface, the column of air around it, on top, on sides, and atmospheric pressure, do not confuse it with the gravitational field strength. It acts in all directions, whether downwards, upwards, sideways. Atmospheric pressure acts in all directions. Now, how can we demonstrate? How can we know that atmospheric pressure exists? We use what you call the crushing gun experiment. And in that case, I will show you, then I explain to you. Before the experiment, this is not how it is. It's just a normal container. You put water inside, then you heat. After heating, you close it. I will tell you why we heat. We heat so that the water inside will produce steam that will drive out air in that container. When air is driven out in the container, what happens is this: there will be no air left. Whatever will be inside the container is what we refer to it as a vacuum. That is a space. And the atmospheric pressure now outside the container will be greater than than the pressure inside the container. What happens is the greater atmospheric pressure outside pushes the container in, and it behaves the way you are seeing there. It looks like it is crushed. It is what we call crushing gun experiment. Sometimes you may not even heat. You just put hot water, then you pour out the water. By doing so, it will drive out any other air inside, making the pressure inside the container to be less compared to the atmospheric pressure outside that crashes, that makes the container crash. So that is it. So it's called as the crushing gun experiment. You can do it at home. It is actually a very simple experiment. Just look for that container that you use to take water, the bottled container for water. So I know most of you fetch water from the river to drink. No problem with that. But go to the highway, you will find one bottle. Then you do the experiment. Don't use a metallic one because it will be hard to crush. Yes, that is it. That's atmospheric pressure. And whenever we are doing a calculation on a pressure in liquids, if we ask you about the total pressure, we have to include the atmospheric pressure. If we just ask you about the pressure due to the liquid, you just apply rho GH. But if we ask you the total pressure exerted on that object, it is the pressure due to the liquid and the atmospheric pressure on top. So look at this example. A sea diver is 18 meters below the surface of seawater. If the density of seawater is 1.03 grams per centimeters cubic, and G is 10 Newton per kilogram, determine the total pressure on him. The keyword is total pressure. If they just ask about pressure, we just apply rho GH with nothing else. But the total pressure, meaning that you have to calculate the rho GH plus atmospheric pressure. Our rho GH, rho is the density, which is 1.03 multiplied by 1000. You get 1030 kilogram per meters cubic times now the G, which is 10 here, times the H, which is 18, plus 103,000. That's what you will get, Newton per meter square. That is now the total. We have included, or we have factored in, atmospheric pressure. I want us to see how we measure pressure. And we have a YouTube manometer and a mercury barometer. which we can use it. In most cases, we don't, whenever we are using these instruments to measure pressure, we don't get them in units of pressure, Newton per meter square or pascals. We get them in terms of height of the liquid used. For example, YouTube manometer, if it is using mercury, it's the pressure of the gas we are measuring, for example, you will not get it directly as 50 Newton per meter square. No, we will get it in terms of the height. Then we calculate using rho GH. Look at this. For example, a YouTube manometer is used to measure the pressure of a gas, and this is the gas in this diagram now. So before the gas is connected to this YouTube manometer, the height levels of A and B were equal. But now after being connected, the height on the other side would be greater than this other side. So the gas has done what? The gas, this gas in which we are measuring its pressure, it has pushed the liquid, whether it's mercury or water, to rise at a given height above the other height of the other arm. So for us to get the pressure of the gas is rho GH. And if the upper part is open, meaning this gas was not only pushing for this height H, but also it was pushing the atmospheric pressure that was trying to push the liquid downwards. So if it is open, the gas pressure will be rho GH plus the atmospheric pressure. I will give you an example. Look at this. Look at this. The gas has pushed and the liquid has risen 20 centimeters above the other height, or the height of the liquid in the other arm. Then we are told we find the pressure due to the gas if the atmospheric pressure is 103,000. Sometimes they give you atmospheric pressure, but this part is closed. If it is closed, please, there is nowhere the atmospheric pressure will participate or will function. Now in this case, the pressure due to the gas is rho GH plus 103,000. Rho is, it is water, so it is 1,000 times 10 times the height, which is 0.2. It is 20 centimeters, but when we convert it, it gives us 0.2. Then you add 103,000. You will get your total pressure because of the gas. What could be, or what would be the height if the liquid used is glycerin of density 1.26 grams per centimeters cubic? I will just take you back. Now, if we use a glycerin that is more denser than water, then what will happen is this: the height will drop. So I will just use the rho GH alone to find the height of glycerin. Rho GH of water is 1,000 times 10 times 0.2 should be equal to, that one we have been told 1.26 should be equal to 1260 times 10 times H. You will get it, the height of the glycerin. It will be 16 centimeters. As simple as that. Now look at this. The diagram below shows a mercury manometer. Some dry gas is present in the closed space. We have a space here. You can see my cursor. We have a space here. If the atmospheric pressure is 105,000 and the density of mercury 13,600 kilogram per meters cubic, determine the pressure of the gas. Now, this side is closed, so atmospheric pressure will not act on this side. The side which is open, this part, is the part now which atmospheric pressure will be acting downwards, pushing the liquid to rise upward by a height of 25 centimeters. And we have been given the atmospheric pressure. So this atmospheric pressure should be equal to the rho GH plus the pressure of the gas. So 105,000 should be equal to, what is the density of mercury? 13,600 times 0.25, the height in meters, 0.25 times what? Times 10 plus the pressure of the gas. So it is simply 105,000 minus into bracket 13,600 times 10 times 0.25. You get it. Yes. That one is so simple. Now, mercury barometer. Mercury barometer is used to measure atmospheric pressure. Yeah, it is used to measure atmospheric pressure. It is the most commonly used. Now that when you put some liquid in a container with an inverted with an inverted tube, atmospheric pressure will push that liquid, regardless whether it's mercury or water, paraffin, ethanol, it will push it to rise upwards. When it rises upwards, the height that has risen will give us, if it is in millimeters, will give us the millimeters of mercury, millimeters of water. Then we use it now to calculate pressure in pascals or Newton per meter square. Or sometimes we just leave it that way. So also pressure, giving pressure in terms of millimeters of mercury is allowed. It can be another unit to measure pressure. But be aware, if you ask to give in pascals, you do what? You use rho GH. Now, depending on the liquid you have used, the height will vary. Mercury will give the shortest height because it is the highest density. Hey. Because it has the highest density. Now, if you use water, it will be very, very long column. You will require a very long glass tube. That's why we don't use water. We use mercury or any other liquid that is denser than water. That will just make you use a glass tube that is shorter. But if you have a long one, 10 meters, you can use water. You know, this mercury parameter only measures the atmospheric pressure. You just place it, then you allow the atmospheric pressure to push the liquid upwards through the tube. Then from there you do what? From there you calculate, or you simply give in that height. For example, in this case, it can give you in, if it's a mercury, for example, it will give you 76 centimeters of mercury. At sea level is at coastal level, that is at the coast. It is always 76 centimeters of mercury. If you use 76 centimeters of mercury, you can calculate it to give you Newton per meter square by doing what? 76 of 100 times 10 times the density of mercury. You will get 103, 360. So at sea level, it is 103, 360. Roughly 103,000 Newton per meter square. That is the density, that is the atmospheric pressure at the sea level. It is the one referred to as the standard atmospheric pressure. So standard atmospheric pressure is 76 centimeters of mercury, or 103, 360. I've given you some steps here that you can use to prepare a mercury barometer. So follow it. And there's a point here. Mercury is preferred in the construction of a barometer to water liquids because it's very high density. Yeah, I don't teach English. Create your own statement. That is mine. Correct the grammar. Now, when we are here now, let's use this question. A student in a place where mercury barometer reads 75 centimeters wanted to make an alcohol barometer. I think in that area there was no mercury. The available liquid was alcohol. And because there was no mercury and any other liquid can function, the student, that person, it should not be a student. Whoever was doing that is not a student. That person decided that before this alcohol finds another use, let me use it to construct mercury. Now it's called alcoholic barometer. It's no longer mercury. If alcohol has a density of 800 kilogram per meters cubic, what is the minimum length of the tube that could be used? So in short, by the end of the day, whether you use mercury or alcohol to measure atmospheric pressure, the value of atmospheric pressure at that given place should be the same. Now, because it should be the same, so we will use mercury because we know that mercury has the height of 75 centimeters. The density is 13,600. So 75 over 100 times 10, which is the G, times 13,600 should be equal to 800 times G times H of mercury. And you'll get that height. It's very long. Look here. It is 12.75 meters. So you require a tube that you're going to invert it, which is 12.75 meters. A very long one. That's why we prefer a denser liquid like mercury. The mercury, another question, the barometric height in a town is 70 centimeters of mercury. Now this is the question I was looking for, and just be very keen, kidogo. The barometric height in a town is 70 centimeters mercury, given that the standard atmospheric pressure is 76 centimeters of mercury, and the density of mercury is 13,600. Find the altitude of the town. Use the density of air to be 1.25 kilogram per meters cubic. Then you have been given there, umeambiwa, the standard pressure refers to the atmospheric pressure at sea level. So there is no much to talk about. Now listen to me here very well. Let me narrate to you a story about this question. This question, a mercury barometer was used in two places, at sea level, then at the highland. I still remember my geography teacher telling me that altitude is the height above the sea level. Now you are being asked about altitude. So in short, you are being asked about the height. Ask yourself, what has brought the difference in the height of the mercury barometer when in the sea level and when in the mountain? It is the atmospheric pressure. It is the atmospheric pressure. So the difference in pressure is the atmospheric pressure. And the atmospheric pressure, just like we said when we were defining atmospheric pressure, we said this. It is brought by the air column surrounding the earth. So I want us to calculate the pressure at, the atmospheric pressure at the sea level and the atmospheric pressure at the mountain. Then we get the difference of the two pressures. The difference between the pressure in the mountain and at the sea level will be because of the air column between it. Then we take that pressure that is now the difference of the two, and we equate the rho gh of the air between the height of the mountain and the sea level. So that air, this is the sea level, this is the mountain. That column of air, its pressure is the difference between the pressure, atmospheric pressure at the up and at the bottom. So, or the bottom and the up. So now, what this there is, take that difference should be equal to rho gh of air. We have g, which is always 10. Then we have rho, which is, we have been told in that question, it is 1.25. So it's very simple. Just to use rho gh here, 70 and 76, get the difference. But remember, the density of mercury is 13,600. And that is nice. So you just have to go all the way until you get 652.8 meters. A very simple one. The figure below shows a person sucking water using a straw. Explain how sucking is made possible. Explain how the sucking is made possible. You know, you guys are just taking soda. The best brand of soda is Fanta. I'm not advertising Fanta, but the best brand is, you know, if you want to test the feeling of Fanta. I don't know why they choose Coke. Fanta is nice. So now, when you put your straw in the mouth, I don't know whether I have a straw here. I don't. Somebody picked it. When you put that straw and then you suck it, you are actually creating a vacuum inside the straw, or you're actually making the pressure inside the straw to be lower compared to the pressure outside, which is the atmospheric pressure. So atmospheric pressure will push the liquid now to rise in the straw, and eventually they will reach your mouth. Try to close the mouth of a bottle, if that is the best term we can use, the mouth of the bottle. Then you try to suck it. You will never get any, because there must be a space in that place to ensure that the atmospheric pressure pushes the liquid to rise up in the straw. Yeah, when one sucks, pressure inside the straw reduces. When one sucks, pressure inside the straw reduces below the atmospheric pressure. That the pressure difference causes water to rise up the straw. Yeah. Now, for mercury barometer to function well, there must be a vacuum inside the space you are seeing. It must be a vacuum. It must not be filled with air. If air is present in that vacuum, then that mercury barometer is faulty. So before you start using it, you have to test whether it is faulty or not. How do you test? You tilt. If you tilt and then the mercury feels it, then it means it is a vacuum, and that barometer is well. If it does not feel, then it means it has air, and that barometer is faulty. Faulty means it's not worthy to be used. It's not good to be used. So this vacuum that is present here, we call it a Torricellian vacuum. It's known as Torricellian vacuum. So that is it. Let me do siphon here. Let me say some people. Let me wacha nistaki watu. I grew up somewhere along Eldoret Uganda highway, where many lorries pass there as they are going to Uganda, and the drivers, for them, that are not given the money to buy the fuel, there are some specific destinations that they are supposed to get fuel. You just go and say, this vehicle belongs to this company, I want to fuel it. So they will never ask you about money. The petrol station will just charge the company from the other side. Now, so there's somewhere these drivers will come and then sell some of the fuel. And the fuel is inside the tank. You cannot turn the lorry to pour out the fuel. But they were so nice. They were applying siphon. They take a pipe, insert inside the container, the tank, where it has the fuel. Then they suck it. After they have started coming out, they just release it to the 20-liter container somewhere there. And it was physics. They didn't know, but they were applying it in the wrong way because the owner of the lorries didn't know. Yeah? But I think they knew. So that was the first time I saw siphoning. Yeah, but now we learn it. I don't know whether it's a mistake. We are teaching you how to siphon so that you go and abuse it like those drivers. But no feelings attached. If you're doing it, please just continue doing them. The nature will judge you. Now, siphon is used to transfer liquid from one container to another. It applies the pressure difference. Look at the diagram here. This is a tube transferring liquid from container A to container C. And you put the tube in container A and you fill that tube with water first to provide continuous flow. If you don't, there will be no water flowing or whatever the liquid. But now if there is water or if there is liquid inside the tube to provide initial flow, then the atmospheric pressure will simply make the flow continue. There must be conditions that we have to use here. Mark these points. We have marked part A, part B, and part C before we look at the conditions required. Conditions under which a siphon works. The tube must be filled with the liquid first. This creates a pressure difference. It must be filled either by pouring liquid to it or you suck until it comes out. There must be a difference in levels in the two containers. Look at this. this container must be lower down compared to container A. The one you are transferring liquid to must be a little bit lower, also to create a pressure difference. The end of the tube must remain below the liquid surface of the upper container. This one is obvious. The end of the tube upper. For example, now, if the tube ends at this particular point B, then there will be no liquid coming out. So the end of the tube must remain below the liquid surface of the upper container. That is siphoning. It does not much. You can apply at home. I used to do it when I was free at home. Siphoning. Just enjoy it. You know. Yeah. The figure below shows how empty tank from water. The figure below shows how to empty water from a large tank into a low-lying tank using a rubber tubing. Explain why the tube must be filled with water before the emptying process starts. That one we have said, to create a pressure difference. Yeah. So soon after the tank begins to empty, the lower end is momentarily blocked by placing a finger at end D. Why? So that your maji container is okay before you move the container that you are transferring to more downwards. Determine the pressure difference between point A and D. Pressure difference between point A and D. This is water, and the difference and the height difference is 2. So rho GH, water is 1000 in terms of density times G10 times 2. That is the pressure difference. What will be the pressure experienced by the finger at point D? Take the density of water. It will be the same thing because it will be, at point D, what will be the pressure experienced at point D? Unless we are given the height between A and B, so that now we get all of these rho GH. They have not given us. 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 But they have asked, what will be the pressure experienced by the finger at point D? Take the density of water as 1000 and the atmospheric pressure to be 1000 Newton per 100,000, that is Newton per meter square. So they want you to give the pressure at this point. Now, what has made the liquid to come out? You see now from I think this one this concept I'm getting it from just right now. Between point A and B, that height is the atmospheric pressure pushing water to rise beyond that height. So actually, the height AB is atmospheric pressure plus now the rho GH of that between point C and D. Okay, that is it. Now, so you will get to at 120,000 Newton per meter square. So I wish you get some more questions on this in using KLB book or any other revision book that you can get. Revise it, see your teacher and anybody else. Now, just slide to the next video again. I'm discussing applications of pressure in liquids and in gases. Thank you. God bless you as you are subscribing and sharing my video all over.